So we ended up last time on our last video on topic 4 talking about context-free languages. We talked about the relationship between PDA, context-free grammars, and context-free languages, and we saw that the PDAs, the push-down automatas, recognize the class of context-free languages, and the CFG, the context-free grammars, generate the class of context-free languages. Okay, so there is equivalence here. How do you show this equivalence? We won't see the full proof here, but I want to give you the gist of it. So to show equivalence, you have to show that you can build a push-down automaton from a CFG, or that you can build a CFG from a push-down automaton. We're going to focus on the first one. How can we build a CFG, a push-down automaton based on a CFG, a push-down automaton that will recognize exactly the same language as the one that is generated by a CFG. Okay, so if we prove that, we have done one piece of the proof. Okay, and so we're gonna just focus on that to give you a little idea about why these two are equivalent. So let's assume the following grammar. S can be replaced by A, T, B, or B. T can be replaced by T, A, or epsilon. Okay, that's our grammar. Now, we want to build push-down automata that exactly is going to recognize the same language as the one generated by this grammar. So the way it works is that you're going to start with the initial state Q0, and the first thing we do is just nothing, basically. We just put the $sign on the bottom of the stack, and then it's not nothing, it's actually very important, and then we load S at the bottom of the stack after the $sign. We're gonna always start with S, right? That's our starting rule. So so we always start, that's our starting variable, so we always start here. So we load S in our stack. Okay, so at this point our stack contains $, and then S on top. Okay, after we load S into the stack, we push S down the stack, we have a Q loop here that is going to be the starting and ending point of multiple loops over the rules. Okay, how does it work? We're basically going to load the rules into the stack. So you can add up here on top of the stack as many instances of these rules as you want, as many as you want to use, just like you do when you actually use the substitutions rule. Okay, so so we're going to do that for each of the rules. So let's start with actually the first one, S A, T, B. Okay, so there are actually 4 rules here, right? We have S A, T, B. We have S substitution B, T, T, A, and T, epsilon, right? We have actually 4 rules. So let's just start with SATB. So how are we going to do that? Well, simply we're going to add to the stack without reading any input. We take S out. We pop S out because we're using S, right? We're using this. So we pop this out and we replace it by ATB. So we take S out and we put B inside instead, and T and A, right? So now we don't pop anything out. We just add T. This is a simple push, okay? So this is substitution. We pop, push, and then push, push. So there you go. So ATB. Why are we doing it? Actually, this one is a loop, so it's going to go straight back here. Okay. Why are we putting them in reverse? Well, because when we're going to use the rule, we're going to start with the last one, right? So you have always to think the stack is kind of in the reverse order that you use it, right? Because you push down first. It's the last pushed is the first popped, right? So now let's take an example. If I want to use now this rule for some input, well, it can actually recognize input A, because A is going to be on top, right? Here. Once this rule is loaded, S is gone because I'm using S, but instead of S, I have now ATB, right? Actually, B, T, A in this order. Now, when I'm going to read my stack, I'm going to read ATB, right? Exactly what I want here. So now I can use that rule to actually recognize A as an input. So far, I don't know if you noticed, but there is no input. No input has been read by the machine, right? So it's kind of like here I'm putting kind of on this side the rules, if we want, and on this side the inputs, the input symbols, the one that are actually read to define what is the recognized language, right? So it's kind of the side here is kind of the side of the language recognized. But of course, to recognize this language, I need these rules. So I'm going to read A. I can actually read A, but as I read A, I'm going to pop A out, okay, and replace it by nothing. I'm just popping it out. I'm just using it to recognize A. The next one would be T. Well, now T is not part of the alphabet, right? You agree that the alphabet here is A, B. So, I cannot read T. I'm going to have to use other rules to substitute T, right? But I can read this A, and now I have, if I do this, you know, if this is my first step, second step, and then my third step here, I have now popped out. So I have to still have my $, B, and T. And that's empty. Okay, so so now I can actually load. I'm not finished loading my rules. I just gave you an example, but if I want to do it completely, I should do for all 4 rules. I'm going to do 4 loops, right? So there is a second loop here. A second loop here that starts by reading nothing as usual, but I'm taking the T out. Right, because there is a T rule here. Taking T out, I'm going to replace it by TA, which means here, of course, AT, right? We said it's a reverse, right? So same thing, I do not read anything, actually do not take anything, it's an epsilon, I'm just here popping T, okay? And this also goes back. So now I have my 2 loops, okay, from these 2 rules. And now I can use that second rule, this one rule here. I can use it let's say I'm loading it now, okay? So I'm loading it on 4. I'm going to take off T, right? T is not really read. It's part of the rule thing. So I can take off T. It's pretty neat when you think about it. Okay, I pop out T and I replace it by first an A and then a T. So I'm going to have B, first an A and then a T. Okay, T disappeared. T was here and it disappeared. Okay. and here we had the A and it disappeared. Okay, so now I have BAT. I have loaded that rule. Now I can keep loading more of that rules, right? I can keep loading some TA. So what if I do this loop like many times? What am I going to have? Well, I'm going to have B A T, like a tower of A and T. Okay, so that's part of the language that is recognized, right? Well, at some point the T I also need to finish it, right? Either with the S I can replace by a B, or the T I can finish it with an epsilon. So I have my two other rules here that I need to load. Okay, I'm gonna try to put all of them on this side, but basically there is well, these two rules are actually straight loops. They don't have any steps like these ones. There is one here that is basically I take a no input, I take T out and I replace it by nothing. That's the epsilon here. I can also read no input, take S out and replace it by B. That's this one. Okay, very straightforward, these two. So that's my 4 rules, okay? There's my rule 1, okay? These are my 4 rules. And I can load these rules in my stack as much as I want, as long as I respect those constraints, right? I have to be able to take a T out. For instance, here I can take a T and replace by nothing, right? This was my step number 4 in my example. In step number 5, I can use that to take T out and replace by nothing, which means I'm gonna have BA, okay? And T is out. Now, now I can read my A again, right? I can read A as an input if I can take A from the stack and I replace by nothing, right? So actually that would be step 6. I take A off the stack and I read A in the same time. Now I can also take B of the stack, right? That's this is part of my inputs, part of my language. So here I need to add another rule, right? It's basically exactly the same thing. Okay, this one can take B off. Okay, so that will be step number 7. And now I have only the dollar sign left. Oh, so I need an exit, right? Well, the exit, of course, pretty obvious. I'm going to just have here an accept state, Q accept, where I do not read anything. I just pop out the dollar sign and replace by nothing, and I'm done. Okay, I need the stack to be empty to make sure that the language I have read so far, the string I have read so far, corresponds to what I've loaded on the rule side. Okay, so I load, and then I read, and then I accept. Actually, to be more precise, I can do a back and forth between loading the rules and reading the inputs. There's no problem. It will always work. So what is the language we've read? So far, we started with S. We replaced S by ATB. Then we read the A. And then we replace T by TAB, then we read another A and then B. Okay, so we've read A, B. Okay, but of course you can read, you can recognize any string in the language that is generated by this grammar. So now we have actually shown through an example. Okay, it's an example, but you see through this example, you can see that the mechanism is systematic, right? I can, for any other grammar, I can write all the rules here as loops. And here I put the language, okay, basically all the alphabet of my language here, with always this kind of pattern with one single loop here over the Q loop. And I know that the language that is recognized by this automaton, that's PDA, will always be the same as the one that is generated by this grammar. Okay, so that's this arrow of the proof, and I think that's enough to get a gist of the equivalence between the two. Okay, so so that's the last part of this chapter on PDAs. I mean, the part of this chapter that is strictly speaking on PDAs. Now we reach again the limit, which is always the interesting time, as we said for topic 3. We're now reaching again the limit. We're talking about now about non-context-free languages. Okay, so non-context-free languages. Okay, so if you remember, we said that 0 star, 1 star is a regular language. Okay. But we said that 0 and 1n is not a regular language. It is a context-free language. Remember that. Now we can see and show that 0n, 1n, 2n is not a context-free language. Okay, and we'll see later what it is. But there are also limits to context-free languages. And as we said, the first for the topic 3, the limits are always interesting because they tell us a lot about the fields we've been studying, and they open us to another field with other results and other theorems. So regular languages, including 0 star, 1 star as an example, and then we have the context-free languages, including 0 and 1n. We now know how to generate this one, and now we have something larger. We'll see later. We don't know what it is yet, but we will see that 0 and 1n, 2n is not in there. It's not a context-free language. So how do we see that a language is not context-free? Okay, well, ideally, it's not context-free. I mean, ideally, obviously, it is not context-free if you cannot build a push-down automaton or write a context-free grammar that generates that language. But it is hard to show that you cannot do that. Okay, as always, like showing something negative is always is often harder. Okay, so how do we do that? Well, just like we did to show that 0 and 1n was not a regular language using the pumping lemma, we're going to use the same pumping lemma to show that this is not a context-free language. Okay, so there is a pumping lemma also for context-free languages, and it is really a similar principle. The idea is the same. Instead of if you remember, for regular language, the pumping lemma was of the form xyz, and we showed that if s equals xyz, if a string equals xyz, you can loop over the y infinitely as many times as you want. You will still stay in the same language, okay, provided that s is greater than a certain pumping number p. Okay, well, here for context-free languages, it is very similar. It's not xyz, it's uvxyz. Okay, so instead of 3 pieces, we now have 5 pieces. So you have to divide s into 5 pieces. And we show that for any language that is context-free, you will stay in the language if you loop over v and y. Okay, so so now we can use that to show that some languages are not context-free. Last time I have shown why the pumping lemma works, this kind of 3 pieces thing, with the loop like that, with this was x, y, and z. I'm not going to show that again for the pumping lemma for the context-free language. It's the idea is very similar, and I don't think it's necessary to go through the proof, but let me give you a little bit of the idea. I mean, at least intuitively, why 5 pieces? Okay, why 5 pieces? Well, you always have why the looping is over the middle pieces. Kind of the typical when a context-free grammar is at its most powerful in some sense is when you have something of the form. Okay, that's a typical form. So from that, if you build the parsing tree, okay, you would have something like that, right? 0, 0, 0. Okay, and then let's assume, you know, you can do epsilon. And then you're gonna have 1, 1, 1. Okay. So you always kind of have like a threefold kind of pattern in the middle, whether you take it here or here. You ever have like kind of 3 parts, you know, 1, 2, 3, and these 3 parts are really this. The pumping lemma as always, like a beginning, we don't know what it is, an end, we don't know what it is, and we don't care too much. And the middle is where the loop is happening. That was the case here. But here the loop is actually of this form, because you can, through this multiple like recursive substitution, you can actually multiply the v and multiply the y. Okay, that's kind of the idea. And in the middle, you're going to have something that doesn't move, because at the end, you're going to stop. You can stop with an epsilon, but you can stop with multiple terminals. And the stop is kind of the x in the middle. That's the gist of it, okay? If you want to see it a bit more clearly, you can say, well, what if I take this triangle, and because it's contained in S, I can actually multiply it and put this triangle here, right? Again, right? And so if I put it here, down here, the same triangle, okay, so I'm going to have additional zeros here and additional 1. Well, you notice that, okay, so this is going to be x, okay, and you'll notice that that was x, that was v, sorry, that was u, v, this part is x, this part is y, this part is z. Now the part that's been duplicated here is really v. You have now 2v and 2y, and x didn't move. X is the same, okay, x is still here. So you have u, v, v, x. I mean, now you have, because it's been multiplied, so you have u, v, v, x doesn't move, y, y, z, okay? So that's kind of the gist of it. I'm not going into the details again because it's fairly technical, and we don't need that. But what we need to know, however, is how to use the pumping lemma to show that this is not a CFL. We need to look at that. Okay, so well, it's really easy. It's the same thing as for the regular languages, right? You're going to see that whatever is the way you divide these into 5, there is no way you loop over v or y without modifying this form. Okay, so this take s equals 0p, 1p, 2p, which is obviously larger than p, right? If you take this, so it has this form, right? I mean, with p times p and p. Whether you take, so you have p, p, p. Whether you take v and y in one of these, you know, so v, VY or VY or VY. It will always be an issue because when you start looping over V or Y, you're gonna unbalance the sequence here. So you're gonna have like 0M1N, 0M1N to K, and it's gonna be K different from N or greater than N because you've looped many times. So that's not gonna work. If you try to put them in the middle, doing a mix of 0 and 1 and a mix of 1 and 2, you can actually manage to have the same number of 1, 0, 1, and 2 total, but they're going to be in the wrong order. Okay? So, and actually this is, by the way, this is I, it's not J. It has to be the same number, right? Which would work here if you do the same number of loop. You would have the same number of 0, 1, and 2 total. But again, this would not belong to this language, because this language requires not just that they have the same number, but they are in this specific order, which you would not have if you start looping over 0, 1 here or 1, 2 here. You're going to have 0, 1, 0, 1, 0, 1 in the middle here. You don't want that. And 1, 2, 1, 2, and 2. Okay. So that's how it works. It's actually fairly easy. You can look at different examples in the book that show different languages that are not context-free. Another one is the one where there is a IJK with I lesser than J lesser than K. It's also not context-free because they are all linked together. Basically, any kind of three exponents like that linked together with a condition that links them is not going to be a CFL. But if you have something like B is A, I, such that I equals J, or J equals K, that's not a problem. That's a CFL. And you can actually easily build the grammar associated with it, and we should do it just for the sake of the exercise. That's not a problem because you can because the three are not completely linked to each other. Does it make sense? So you don't have the same constraints as you had here. Okay, so either these two are linked or these two are linked. Okay, so yeah, we can build the grammar associated with it. Actually, let's just for the exercise build. I mean, you can basically have a grammar for each, right? So the case where these two are equal, and the case where these two are equal. Okay, and then you can just have two options from the starting point. Okay, you can pick. So let's write B1 and B2. So the grammar for B1, where these two are equal, would be the following, right? You want the same number of A and B, so you're going to have A well, you have two parts. You have this part, let's say A, and this is going to be part B, okay? And A can be replaced by AAB as many times as you want, okay? Or you can stop. And the B part can be replaced by for the B part, you can have as many C's as you want, or you can stop, okay? And you can define a very similar grammar for J and K are the same, right? It's going to be very similar. And then you can define a grammar that combine both and says, well, you can either go, from S, you can either go through JB1 or JB2. Okay, I'm kind of using some shortcuts here, but that's the idea. So it's easy to build such a grammar, but this is completely different from this when you are interested in context-free languages and context-free grammars. Okay, so that's the pumping lemma and the limits of context-free languages. So we've seen some context-free languages that are not some languages that are not context-free. I'm just going to give you one last example for the sake of completeness. Let's say C equals WW such that W is belongs to this, and that's also not context free. You can check that. Okay, so that's for the limit of context free languages. Now the last part of the book I'm going to treat in a different video because it's a whole other topic, and it's a little bit tricky. It's on deterministic PDAs. Okay.